broad overview of a lot of topics we will dig deeper into later. Do a bit of refresher, do a bit of, okay, let's turn our minds to do some chemistry. Just a couple computations, basically algebra applied to the world of chemistry, just to get the chemistry juices flowing, as it were. And hopefully might get a chance to take a look at a particularly interesting exothermic irreversible reaction, because there's, I don't know if anybody you follow it, but there's scheduled to be a Starship launch at 4 p.m., which is a great combustion reaction we could take a look at. So if it goes off, then we'll tune into that right around 4 if I could get the timing right. So that might be fun. Okay, and then we will also take a look at MATLAB. I've got some slides for that as well. Just basically what I showed you last time, but in slide form. So I'll kind of highlight a couple things, and that'll be on Moodle for you to see as you go to do any of these assignments, which, by the way, you can do in advance if you'd like. There'll be that material there for you to summarize what we did off slides last time. Okay, so a few environmental cases where we're going to see the type of chemistry we're talking about. And a lot of this really comes down to equilibrium chemistry. So almost everything will be related to what we call equilibrium. Of course, we're going to touch on a few different types of reactions, and I'm going to highlight that a little bit today. But a lot of it, what we're really learning today and what we're going to make use of in environmental systems will be the equilibrium side of things, where we have reactions that can proceed one way or the other, and there's going to be some thermodynamic explanation as to which one's favorable. Do we need to put energy into the system to make it happen? Are we going to get energy out of it when this reaction happens? That type of stuff. Okay, so one would be carbonate. So the carbonate system is kind of everywhere, and we are breathing it now, right? We breathe in oxygen, we breathe out CO2. CO2 being carbon dioxide. When that dissolves in something liquid, like our blood, it becomes carbonic acid, which is H2CO3 right here. So we can even say this is going to be CO2 plus H2O will be in equilibrium with, and as you can see, if you just simply add an oxygen and two H's, you get H2CO3, right? So when CO2 dissolves, we get carbonic acid, which is H2CO3. So we're going to talk a lot about this. We will probably talk first about it in terms of acid-base chemistry in a few weeks. And then towards the end of the semester, we'll come back to the gas dissolution and how a gas exchange into an aqueous system will affect all this chemistry that we've been talking about. And what you'll find is we could talk about it a whole lot, even just to start off the class and learn a whole bunch about chemistry, and then it'll affect every system we look at. So it kind of doesn't matter if we talk more about it at the end and say, oh, look, by the way, as you're dealing with carbonate, that's going to affect how your metals behave. You know, it's just going to be kind of throughout the whole deal. Okay, so it's quite important. You might have heard about it. You probably have drank carbonated beverages, right? So if you put in Mentos into Diet Coke or something, have this nice explosion. Really what's happening is whatever the Mentos is doing, that little piece of candy, it's allowing all the trapped carbonic acid to go the other way and come back out as CO2 gas. And suddenly it's fizzing. It's fizzing quite violently, and we have a little explosion. So as we think about soda, we will learn that carbonic acid dissolves, we can get more CO2 dissolved into something acidic. Or rather, since this is the acidic form, if we acidify our soda, then it can stay in that dissolved state a little better without off-gassing. Or maybe that's not even the right way to say it. Maybe it's ready to off-gas if we unseal it. If we put it in a basic form, we'll learn later the protons will come off and we'll end up having a lot of CO3 minus, or maybe HCO3 minus, and because it's charged, it can't come off as gas. So it's the H2CO3 that can come off as gas. So what do? We add phosphoric acid to every soda, basically. Sometimes you might see citric acid, but I think in the States it's almost always phosphoric acid. It's pretty food safe, but it's quite acidic. And that there's a couple things there. One is it keeps the CO2, and I've also heard, this might just be some silly wives' tale, I don't know, but I heard that it also kind of burns your throat just a little bit so that you don't have a gag reflex for how much sugar you're drinking. Yeah.
So in order to keep a carbonic acid from volatilizing into a gas and then water, you need to include another acid so that it doesn't decoagulate?
That's approximately right. What we'll see as we look into the chemistry of the carbonic acid system is, by default, if you just have, let's say, natural rainwater with nothing but CO2 in it, CO2 from the atmosphere, the natural pH will end up around 5.6, something like that. So we'd have to add a whole bunch of CO2, and it'll drop the pH a little bit, but it's not a strong acid, meaning those protons are not necessarily going to be released into the solution and make it acidic. So it'll be a slightly acid rain, not strongly, if that makes sense. So that we can adjust the pH, and it'll change how the CO2 is acting in a dissolved phase. So we can add some strong acid that's going to force the system over to one direction and affect this other acid. Okay, so this is a great depiction, a great question there, great depiction of how the different systems will affect each other and how the equilibrium dynamics are going to be important. So that's just one example there. Another might be, let's say, dissolution and precipitation of calcite. This is some people voiced a lot of concern about what's going to happen in our oceans if our little diatoms and things, are they going to be at risk if we increase the CO2 in the atmosphere? That will in turn slightly acidify the oceans. Oh no, we are relying on CO3 2 minus in the equilibrium reaction to form the calcite, which these diatoms are producing their shells with. Now, that's not the whole story, thankfully, because if we're adding more CO2, even though we are decreasing, we're shifting the pH a little bit, and therefore decreasing the fraction that'll be in this form. We'll come back to all this, so you'll see why that makes sense later. But even though that's happening, we are also increasing the total amount of CO2, so it's also counterbalancing. So it's promoting more possibility to form it. It's not so straightforward to say that it will necessarily prevent the formation. So my point is there's an equilibrium reaction here, and oftentimes I would write this as a forward and backward here. The book that I took that from was they just put in equals to mean the same thing. Okay, another possible type of example, and that would be dissolution and precipitation, as well as the carbonic acid system. That's why I kind of reordered this a little bit. It's like that's also the carbonate system, but it's also like a precipitation and dissolution reaction. Another type would be complexation reactions. So if we have iron in water, well, what happens when the iron reacts with water, the water will actually dissociate into OH minus and H plus, and the OH that used to be a minus will attach to the iron. At that point, we're left with an H plus. So this is the source of acid mine drainage. When these types of minerals get oxidized and then they are complexed with the hydroxide that's sitting in water, it forces the pH down because it's releasing a lot of protons. Okay, so we'll look more at that. Like I said, each one of these categories we're going to touch on to one extent or another. Some other reactions include redox reactions. Redox is the short term to say oxidation and reduction, or reduction and oxidation. Redox just sounds a lot easier than oxred. So redox reactions, these are inherently a transfer of electrons. So whenever some molecule or element is grabbing and taking away someone else's electrons. That's an oxidation reaction, or vice versa. You could be having a reduction reaction where it's forcing the electrons onto somebody else. So that's redox. All sorts of redox reactions exist, and these are the ones we're going to split and do half reactions with, and have electrons involved when we're doing the calculations. Of course, we don't consider electrons freely floating in water to be a real thing necessarily, so we always have a net balanced equation at the end of the day where there's no electrons hanging around. But like I said, we'll get there. We'll talk more about that later. Iron oxidizing to rust, basically going from Fe0, which would be like the solid, we call it zero valent iron. Fe0 will oxidize into Fe2 plus and Fe3 plus, and this is the process we know as rust or rusting, right? So then we get iron oxides, which are kind of brownish red, and it's no longer metallic like the zero valent. Okay, gas partitioning is another topic. Again, back to CO2. How much of that CO2 is dissolving into the water? What are the factors at play there? Does not have to be just CO2. It could be hydrogen sulfide, for example. This is the stinky one. This is the rotten egg smell, and it's a very good thing that we can smell it so strongly, because it is extremely toxic. And it turns out that we are so sensitive to it that we can smell it far before it's at toxic levels for us. So, the theory is that we're sensitive to it so that we're not eating rotten stuff, because rotten stuff is often bad for us. Plus, this particular substance, H2S, will be quite toxic if you were to ingest a lot of it, or be exposed to a lot of it as a gas. Okay, so hydrogen sulfide, it's produced in anoxic situations. So if you have a wastewater treatment system and a lot of organic material that our DNA and stuff has some sulfur in it, if you have the right processes, you might end up getting some hydrogen sulfide produced. In sewer systems, this can be a problem. It can build up, and it's a potential hazard for any workers, but also just the smell of it. And it's corrosive and could kind of harm some of the sewer system itself. So you have to design with the right concrete, things like that. You'll also potentially smell it out in marshes where you get so much organic matter and activity that it goes anaerobic, takes all the oxygen away, and then the decaying and the digestion of the materials, you end up forming a bit of that. Okay, a couple more examples. We're not really going to touch on these too much in this class, but it still is an environmentally related equilibrium problem to look at absorption, or more specifically adsorption. This is kind of like when you take some material and you stick it on, you adsorb it onto something. It's like Velcro. Some things are sticky, doesn't mean it can't come back off, but the deal is you can, let's say, treat water with an adsorption column, and it's as if you have this big wall of Velcro and you're sticking a bunch of fluffs on it. Eventually, it's not going to work anymore and everything will pass because the sites are used up. Or you could take it off and clean it and then refresh it and bring it back and catch more stuff. So that's kind of the adsorption reactions are kind of like that. And you'll have some equilibrium between how likely is it for these to fall back off versus being added back. And at some point you reach an equilibrium where you're not really going to get any more or less on that surface. It can also be true for organic matter as it interacts with different metals and things in the environment. So when we talk about metal complexation, we'll probably talk a little more about that part. Okay, so that's kind of a big picture, maybe something I could have walked us through last time, but those are the general topics we're going to be kind of dealing with or diving into over the course of the semester. And I wanted to just give a bit of a flavor for the types of systems we might work with where we'll see some of the chemistry. Of course, that's nowhere near exhaustive for any of those. All right, so let's get back to some of the basics in case you haven't seen it in a while. I think you know all this, but I'm just going to repeat some of it, and perhaps something will click today that had always bothered you before. When it comes to dealing with chemistry, we almost always have to, at some point, use molar units. And the reason for that is technically it wouldn't have to be molar. We would just have to use a number comparison. And moles just happen to be the convention. We could use dozens instead of moles. So 1 dozen, is 12, right? What if I were to say 1 dozen is actually 1.2 times 10 to the 0? Have you ever thought of it that way?
1.2 times 10 to the 0?
Yeah. Or 10 to the 1, excuse me. Yeah, 10 to the 1. 1.2 times 10 to the 1, which I have written there. So, have you ever thought of it that way? Does that connect a little better with Avogadro's number now? The 6.02 times 10 to the 23rd? It's like, that's all it is. It's just a fancy number. Sometimes you could say a score means 20, right? It's not really used very often, but that historically, that's 1 score was 20 of something. So you could use score. The point is, we're just using moles as a way to say it's a lot of this one thing. We buy a dozen eggs because we're not really going to go and buy 1 egg typically, right? It's convenience. So when we do chemical reactions, we often have to compare the number of things interacting. And we know, because we know a bit of chemistry, that the weight of a given atom or molecule does not correspond very well with the number of them, right? But the chemical reactions only care a tiny bit about the weight, and that's just in obscure cases. Usually the actual reaction is a 1-to-1 or maybe a 1-to-2 or some variant of a stoichiometric, meaning the numbers basis change or occurrence. So we have to work on the numbers basis, which is why we have to bother with all the moles. So if in the past you've always been just really frustrated, why does this even matter? Well, for the civil engineers that I teach in EVEG 3110, I use a silly analogy. Well, you wouldn't go and compare on a mass basis how many eggs you need to egg a car, right? You take some number. And if you're going to be really, really nerdy about it, maybe you do 1 for every windshield or something. I don't know. Don't do it, of course. But you wouldn't say, okay, the car weighs 1 ton, so I need half a ton of eggs, right? That doesn't make sense, right? You would do a numbers comparison. So just like eggs and dozen, moles and molecules, right? That's the deal. Okay, so hopefully that's just repeating the obvious and all that. Atomic and molecular weights, we're going to deal with those, of course. And just a quick note, if you have something like oxygen atomic, would be just an O, which doesn't usually exist that way. O2, that's molecular oxygen, what we might call. O3 is ozone. And of course, we can calculate the molecular weight for each one of those given the atomic weight. So you should all know that. By the way, these are called allotropes. So carbon allotropes include diamond, graphite, graphene, fullerenes, which are the Buckminster fullerenes. Are soccer ball shaped carbon things. I've done a lot of research on those. They're fun. Okay, so that's a few fundamentals. Going a step further, let's make sure we can do a couple of problems here. So if I asked you to go into the lab and prepare me 250 milliliters of a 75 millimolar sodium solution for an experiment, and I gave you some sodium chloride, NaCl. How much mass do you have to weigh out for that? Yeah, assuming you're adding that to pure water. Go ahead and calculate that. And I'll go through it with you, so no worries if if you haven't done anything like this in a long time. Sometimes it takes a few minutes. Like, what am I doing?
This would be mass and grams.
Yeah, let's do mass and grams, please. So first thing to know here, in case this wasn't clear, that lowercase m, that's millimolar. And a molar, the capital M, is moles per liter. All right, so the first thing I look at is I take the 75 millimolar and think to myself, well, let's put that in moles per liter since we can do the atomic weight and everything in moles per liter or in grams per mole. It would just be nice to have everything in moles, so I divide it by 1,000 because we'll have 1,000 millimoles in 1 mole. So we can just simply move that decimal place 3 places and say 0.075 moles per liter. By the way, how many of you already got the answer in your board already? Okay. How many of you are like, ooh, haven't done this in a while? Okay. So not a waste of time for at least most of you, right? It's good. Okay. So at this point, what I'm doing next, I'm thinking to myself, well, we have this concentration we're targeting, and at some number of moles in a liter, we also know we have some volume of the solution. So if we put those two together such that the units are going to cancel, we can get the number of moles we're after. And so effectively, the first thing I'm answering is, well, how many moles of sodium do I need in this solution? So how many moles of Na plus do I need? Before any of that, I went ahead and wrote down the molecular weight for sodium chloride because that's what we're going to be adding. So we're going to need that at some point. But I haven't used that at all yet. And that was just before I thought about anything else, I was scribbling that down. Okay, so now what I'm asking myself is how many moles do we need in this solution? And so I take that 0.075 moles per liter, multiply that by how many liters we have to get rid of the liters. And you'll notice I had to convert, I didn't do this, but the 250 milliliters, that will be 0.25 liters. Again, that's the milli to normal liters. From there, I can go ahead and multiply those two. The liters will cancel and we get 0.01875 moles. Did that in a calculator. We get that value. So now the question is, how does that relate to, so that's the moles of sodium, Na plus, that we want. So how does that relate to the sodium chloride? So I could be a little more precise and add that here. Sorry, I should just write it here instead. Okay, from there, one thing we can recognize is when we dissolve sodium chloride, I didn't really give you this information, but hopefully you might recognize salt, table salt, sodium chloride dissolves pretty well in water, right? So if you add some of it to water, it's probably all going to dissolve, okay? If we go really crazy with it, yeah, we'll reach some solubility limit. We haven't touched on any of that yet, so we're not just going to assume this all dissolves. All right, so that should then give us, for every 1 sodium chloride we have here, we'll get 1 sodium and 1 chloride. Cl minus. All right, so that means there's a 1-to-1 relationship for the sodium chloride and the sodium, and that's where our chemical reaction comes into play, right? That's why we're making a molar comparison here. All right, so that means we need exactly 0.01875 moles of sodium chloride added to our solution. So now all we have to do is say we need this number of moles of sodium chloride, and we can simply multiply that by the molecular weight for sodium chloride and get our answer, because the molecular weight is in grams per mole and we have moles, right? So if we do that, multiply this by the 58.54, 45. And again, we could be a little more precise than I started here and say moles of sodium chloride to avoid confusion. Whatever the answer to that is will be the amount we need to add. Okay, so we'll go ahead and do that. Times, what's it, 58.45. So it looks like we need about 1.1 moles. So I'm just going to go ahead and say, well, since it disappeared, we're just going to go with 1.1 moles.
be grams.
It is supposed to be grams. I was thinking to myself, that's a lot of moles. Yeah, thank you. Exactly right. Okay. So less than a teaspoon. I think a teaspoon is something like 5 to 10 grams of sodium chloride. Maybe I'm off, but it's not a lot. Not a lot. Okay. How does that feel? Make sense? Done it before? All right, let's do it briefly with sodium hydroxide. And as you're doing that one, think to yourself, if you can recognize something about that, why sodium chloride might be a better choice. And that'll bring us to something we're going to talk about in a little bit. All right, so hopefully you kind of noticed we already had most of the problem solved because we already solved for like how many moles we needed of the sodium. So we could just take that same number, 0.01875 moles of sodium, therefore moles of NaOH, if this is our reaction 1-to-1. Sodium hydroxide would give us a sodium and a hydroxide, right? So then we just take the molecular weight for sodium hydroxide, which is, we just don't worry too hard about the far decimal places. It's basically 23 plus 16 plus 1, so that should be 40. So if we do that, turns out we need 0.75 grams of sodium hydroxide. Now, any thoughts on why in a typical chemistry reaction or lab setting, why the sodium chloride might be a better choice?
Yeah, which is a strong base.
Yeah.
It's harder to work with.
Yeah, so you might not want to make your solution strongly basic. So if you're adding a strong base, that's no good. So, or maybe no good. Of course, sometimes you might want to. So the OH minus, for every 1 mole of sodium hydroxide we add, we're adding 1 mole of base, essentially. Now, another reason why you might not want to work with it is it's pretty hazardous. Of course, it's like people work with it all the time. It's fine. You can be safe with it. But it's one of those things where if you happen to get a speck of it in your eye, like a pellet, you work with like kind of chunks of it. It's so, I think it's hygroscopic is what it's called. It really, really, really wants to react with water and dissolve. And it will basically dissolve your eye pretty quick because of that. So you really, it sounds so basic of a thing to work with, and people work with it a lot in labs. But yeah, you definitely want to be careful with that one. So, okay. Well, good. I'm hoping that I can give you some flavor of the chemistry along the way and just kind of start getting a feel for, okay, what's up with NaCl versus NaOH? What's the big deal? to start just adding in your mind a little more context to like what all might be going on. Okay, one other thing real quick. I want to make sure you're comfortable with this as well. This is, instead of adding a mass of something, adding a volume. So we have a concentration, similar target, or same target rather, 250 milliliters of 75 millimolar sodium. And what if we had a 1 molar, so the capital M, again, that's moles per liter, NaCl solution? What volume of that do you need to add to find your goal? I've got a little hint down below I'll reveal in a couple minutes. So take a moment, make sure you get your mind around these types of problems. All right, so same questions again. First, how many of you bored already? Okay, how many of you are like, oh, why is this hard? Why don't I remember this? Okay, yeah. So this is why I'm doing it today, is because ideally you're all already bored. Hopefully, right? I'm not trying to bore you, and I'm not mad at you for being bored with my lecture or anything like that. But this is stuff that I know that you've learned it, right? It's not that big a deal, but when you step into a lab or step into a chemistry assignment and you haven't done it in a while, I want to just be very, get us all on that same page with the simple stuff before we really launch into too much else. So kind of the fundamental formula for this type of thing is actually a very simple mass balance. In fact, we could have looked at the last one that way too. There's a dilution formula, if we want to even call it a formula. It's the amount of volume we have times the concentration we have in one solution will be equal to the volume in a second times that. We can make that relationship to say if we need some amount of N, of the concentration, or of the moles rather, we'll say, we can say we need that 0.075 moles per liter times some volume, and say that can be, so let me write it this way. Write it rather than speak it. So 0.075 moles per liter of our sodium times the 0.25 liters. That will give us, if we look at the units will cancel and just give us moles, right? So N being a molar concentration down here. That means we can get the amount we need to add will simply be the 1.0 moles per liter times some unknown volume, V2. right? So if this is V1, N1, and this is N2, that's V2, right? So we can use that very simply and say, oh, okay, let's do that. And now that I'm looking at it, we're just going to multiply that 0.075 times 0.25, which I think we've done a few times already, and then divide it by 1, which is going to make it the same thing. So I think V2, if I'm not mistaken, should be that same number we were looking at earlier, just happens to come out again. So that would be almost 20 milliliters, right? 18.75 milliliters. Can double check that I did that correctly. So 0.075 times 0.25. Yeah. That was actually an accident. Then it worked out like that. Okay. Does that make sense? All right, great. Okay, so that's kind of all the low-key review stuff I wanted to handle, just to make sure we're kind of warmed up on it. We're actually going to come back briefly. I might do that again in MATLAB later or something like that, just to kind of fool around with it a bit. Okay, so one thing that might have reminded you of is we need to know our units, right? So milli versus micro. So if I were to do the same problem, but I wrote it as, you know, how many nanograms or micrograms or moles, right? Micromoles per liter. Make sure you're familiar with all that, right? It's, need to know it. Another little thing we could do. I don't think I'm going to have us do this problem right here in the moment, but a couple other conversions you generally should know with anything water or chemistry related is we have 1,000 liters in 1 cubic meter. That's the volume comparison that you're not going to find on a little lookup chart like that, but it's probably something you should know. That also means that if we convert between milliliters and cubic centimeters, that's a 1-to-1 situation. Now that might feel really weird because a liter and a cubic meter are related, but now we have milli versus centi. So don't forget that when you do any conversion, you're going to square or cube rather, the conversion factor along with the unit. So I'm just going to say 1 cubic meter is equal to, let's use centimeters. 100 centimeters cubed. And what I can do here is say 1 meter is equal to 100 centimeters and cube like that. Right? That's the right way to convert it. So then you see that 1 cubic meter is actually equal to 100 to the 3rd cubic centimeters. Right? So whenever you do your conversions and things, keep that in mind. Here's a little challenge if you want to. I think I'm going to pass on it since we've already spent a little while doing this kind of stuff. If I told you how many, the density of water is 1,000 kilograms per cubic meter at 5 Celsius, I could ask you how many grams are in 1 milliliter of water. Turns out that's exactly 1 gram. So it's quite convenient, but you could prove it to yourself and kind of refresh your memory there if you'd like. But that's also a good way or a convenient way to kind of test if you're ever in a lab and you want to test, is the scale accurate? Is my pipetter accurate? You can measure water, take the density lookup table and say, okay, well, it's close to 1 gram per milliliter, but it's a little warmer than 5 Celsius, which, 5 Celsius is what, like 40 degrees or something, Fahrenheit. It's a little warmer than that in the lab, so you're going to have to do some conversion, but it's going to be pretty close to 1 gram for a milliliter. Okay, so going to cover some broad brushstrokes, basics about different concentrations and a few different concepts about the chemical systems we're going to talk about. So again, a little more review here. Expressing concentrations, it's all about describing how much stuff is in some other stuff, right? Pretty straightforward. We can do it in a lot of ways, a lot of different denominators, a lot of different numerators, right? We've just talked about moles. We could do mass. We could say milligrams per liter, moles per liter, liters per liter, use some sort of volume. On the denominator side, of course, we could do liters, cubic meters. We could do it by weight. Sometimes we do it by proportion, right? So you've probably seen ppm, parts per million, right? Did you know that, let me rephrase that. So you're familiar with that. It's like parts per million, parts per thousand. Have you ever heard of parts per hundred? Anybody? Nobody. Pennies, that's a good call. Actually, all of you have learned parts per hundred way before you learned anything in college. Because parts per hundred is percent, which is where we get cent, right? 100. So parts per hundred is the most familiar thing almost ever for you, right? So if you have any trouble thinking about or conceptualizing what's going on with parts per thousand or million or trillion or whatever, remember parts per hundred is percent. That's how we use it. And you could do percent by volume, you could do percent by mass. It's parts percent, right? Percent. And we just drop off the parts because it's just sort of implied. Okay, so you've actually done this before, and truly, even the parts per thousand abbreviation is a little percentage with an extra zero on it. Okay, so once you let that kind of soak in and you see that, hopefully that becomes a little easier. Like, oh, okay, we're just dealing with a percentage. I'm just going to move the decimal place a few times and account for it appropriately, right? It's the same concept. You can do it. It's not quite as convenient sometimes if you're like on the 100 scale and we're so used to saying like 100% is everything or whatever. So I guess 1 million ppm is like saying 100%, right? It just doesn't feel so natural. Okay, so I just wanted to kind of remind you of some of that, give you that parts per hundred concept. Cent, like century, is the Latin root for 100. Okay. All right. A few other things we could look at in terms of kind of how volumes versus mass correspond. So oftentimes, especially when it comes to water, we can do certain specific mass and volume correspondences. So if you are assuming a water solution density of 1 kilogram per liter, all of the following end up holding true. So 1 milligram per liter would be the same as describing that in terms of, let's say, 1 milligram per 1 million milligrams of water. So this is all ppm. So 1 microgram per liter is 1 ppb, and 1 nanogram per liter is 1 parts per trillion. Of course, keep in mind sometimes the T will be 1,000 versus trillion, but yeah. So just a few convenient things given what we just talked about. Okay, so another concentration unit that we probably haven't encountered too much before, we're going to make a note of it here and describe why it's important in chemistry, and then probably not do too much with it because I want to keep things a little simpler and focus on the equilibrium reactions themselves rather than the details that make it really precise or that in some cases we have to deal with, but not all the time. Okay, the first one being molality. So a lot like molarity, but there's an extra L instead of the R, right? So molality, this is essentially a concentration by mass instead of by volume. So if we take a step back and find that time when the water density is exactly 1 kilogram per liter, it makes no difference. However, if you take my 1 liter of water here and dissolve a kilogram of salt into it somehow, you have very likely just changed the density of this solution, right? Even if the volume didn't change much, the mass certainly did. So At that point, you have now altered the molality of your solution. And so that does become important sometimes, especially for seawater or brines, things like that. Having the molality is something that, as this little book excerpt I have says, physical chemists are concerned with careful measurements, use equilibrium constants. They usually refer to the molal scale for that reason. So sometimes it is important. In a similar way, sometimes we will work with activities and activity coefficients. I think I'll talk a little bit about that next time. Likewise, we're going to say, okay, sometimes this is important. Here are the cases, and here's maybe an example of how to solve for them. But for the most part, we're going to make the assumption that we're not going there for most of our problems. Okay. So a few other types of concentrations we might express. Mole fractions are pretty common. That's basically the fraction of X or fraction of a system that is X is the mole fraction of X. So moles of I per total moles, for example. We could talk about normality. So you might, if you've done any work in a lab or something, you've often will see this with an acid. You'll have a 6 normal sulfuric acid or something like that. What this is referring to is almost exactly molarity, except that it's referring to the amount of events, the equivalent amount of events that happen given that concentration. So, for example, if we compare two different strong acids, H2SO4 and hydrochloric acid, so sulfuric versus hydrochloric, we would find that sulfuric is essentially going to give up 2 hydrogens and a sulfate, and HCl is just going to give up 1 proton and a chloride, right? So we can see that one of them is giving up 2 protons, the other is giving up 1. So an equal concentration will have a different impact on how much acid is added to the solution. So normality is a way to normalize that and say, okay, per proton contributed, the equivalent is 1 normal, meaning 1 mole per liter of protons given. So half of a moles per liter of sulfuric acid would be the same as 1 mole per liter of the hydrochloric in terms of how many protons they're sending into solution. So that's the deal. That's normality. It doesn't have to be the protons. We could use it for electrons. And that kind of brings us to the concept of equivalence, which we often use for charge or electrons. So mole equivalence of charge, mole equivalence of electrons, things like that. So we could define normality as the grams of some solute divided by the grams of equivalent weight of the solute times the volume of the solution. So basically just the description of viscosity, right? What's happening versus how much is there. Okay, equivalent weight is another thing we can do. If we want to compare a couple different types of stuff, we might take a look and say, well, maybe we want to know how much chlorine we're adding, like free, active, reactive chlorine, and compare that to are we doing chlorine gas or are we doing sodium hypochlorite? And we might just compare that based on how much reactive chlorine we have. So the equivalence then could be something like that. I'm going to take a very quick pause to see if we can watch some chemistry in action.
I just have a quick question.
Yeah.
So, is it very common for sulfuric acid to fully dissociate? Because does that really only pertain to like the full dissociation of an acid?
That's a good question. So, sulfuric acid, you're right to recognize that it can also partially dissociate into HSO4 minus, and that's just giving up one H plus at that point. And that might be in equilibrium with H2SO4. So you're exactly right, but it is common for it to fully dissociate unless your pH is really, really low. So it turns out that we'll talk about this more when we get to the acid-base stuff, but the pKa, the equilibrium constant for the second deprotonation, is somewhere between 1 and 2, I think. So unless your pH is like down around 1 or lower, then it almost basically all dissociates. It's a very, very good question. You're getting me onto topics we hadn't prepared to talk about yet today. This is good. Okay. All right. So a couple other pieces. We have another concept that we need to hold as true for basically all of aquatic chemistry is the electroneutrality constraint. That just basically means all waters have a net neutral charge or net even charge. When we count up every positive charge and every negative charge, they should sum to 0. And that's quite important because that will limit a lot of what we see in terms of acid-base or in terms of all sorts of equilibrium chemistry within an aqueous environment. If there's any charged species involved, we recognize there has to be some accounting for what's happening. Anytime there's something positive added, okay, where's the negative showing up? Are we causing some change in the acidity given what's happening, or like what's the deal? So we can use that. We can also use other mass balances or proton balances, different ways of figuring out what all's happening within our solution to describe or to solve a system to see, okay, how much of X do we need to add? Okay, a few miscellaneous terms we will come back to. I wanted to just mention them here while we're talking about all these concentration units and things. Milligrams per liter as such and such. So as calcium carbonate, this is one of those equivalents. This is often for alkalinity or hardness type stuff. We're basically going to say, okay, calcium carbonate, CaCO3, has some very standard known amount of contribution to alkalinity. And if we use some other chemical, well, we might as well compare it to that because it ends up being very convenient. Okay, so it's kind of like doing the whole mole conversion just on the front end instead of the back end is kind of the point. Alkalinity, mentioned that is defined as the sum of the bases that we can titrate with a strong acid. It's kind of like the acid neutralization capability of the water. So we'll talk about both of those a bit. Hardness, a similar concept. It relates to a lot of it. It is the sum of the divalent cations. That's mostly magnesium and calcium. Those are the typical minerals. That's typically what's responsible for if you have hard water and you get like the mineral scaling on your sinks and things. It's usually some calcium and magnesium deposits, probably hydroxide deposits. Sometimes we'll use milligrams per liter as P or as N. And that's typically if we have different forms of phosphorus or nitrogen and we're trying to do an overall nutrient balance, and it's really the moles of N in the system that we care about. But as engineers, we're often trying to talk about it in mass, so we've done it into milligrams per liter. And if we want to compare between ammonia and nitrate and nitrite, well, we can do all those calculations and then report it as N, as if we're just counting the nitrogen within that compound and just dealing with all that. We can do the same thing with chlorine. Sometimes we'll have it as Cl or as Cl2 when we're talking about like disinfection type of stuff. Okay, and I don't think don't think we've got the live event here. I don't think they're launching yet. But you can imagine a rocket launch is a good example of a lot of chemistry happening, not necessarily aqueous, but one other thing I wanted to talk about is the difference between an equilibrium reaction and an irreversible reaction. So you can almost think of it as, is it reversible or not? And when I say reversible, I mean within kind of a typical thermodynamic context, right? Or typical system, is it going actively back one way and the other? And certainly an explosion or burning of rocket fuel is certainly not a reversible reaction in that sense. It's going in one direction, going to combustion products and releasing a lot of energy as it does so. So we'll typically describe these reactions with either an arrow or a both ways arrow. Sometimes one of the books I used will have just an equals. Now, what was I going to say? Okay. Sometimes we might just describe a reversible one as a partial ionization. In fact, that question about the sulfuric acid was great because that was the question, right? It's, oh, does sulfuric acid, does it partially dissociate? So if you see text like that, we can say, oh, it's partially ionizing or partially dissolving. That clues us into, oh, there's some equilibrium here. And in fact, I also mentioned sodium chloride. If we get enough sodium chloride solid, we could reach an equilibrium between the solid and the dissolved forms. But that is so soluble in water that most practical cases we're never near that, right? In that case, when we describe that, like in the problem earlier, we might as well just put a forward arrow. Even though technically we could get there, most of the time it's going to be forward. So I don't want that to confuse you too much, but I'm just trying to give you an appreciation for, depending on what's going on, some of these things could act like either, especially when it comes to like precipitation. The real deal there is, it's just like, are you adding a block of sodium chloride this big to my liter of water, right? That's not usually what we're doing in a chemistry experiment. So if we're not adding that much, then it acts like a forward reaction, right? It's completely dissolved. Okay, so we'll talk a little bit about that and how to find that out when we get to that point in the course. So equilibrium then is what we say, or what it is when we reach the point where both rates, forward and backwards, end up equaling each other. So the rate of production of one thing, let's say for our HOCl here, this is hypochlorous acid, that's bleach, right? When we have the same rate at which that's dissociating into H plus and OCl minus, as the H plus and OCl minus in solution are reassociating into the hypochlorous acid, when those two rates become the same, we have reached equilibrium. So we could describe that with a forward reaction and a backward reaction. When they meet, we're good. A lot of these are pH dependent. So if you found an equilibrium and then you change the pH, you will move to a new equilibrium. Okay. A lot of our class, we're not going to worry too much about how long it takes to get to equilibrium or the process in between. So a lot of times we're just going to say we're at equilibrium and we're figuring out what's up with the system at equilibrium. In fact, in nature, it's very rare to have true equilibrium, but it's often a good approximation. So, there's tons of different equilibrium reactions we can think about in my water bottle. And, as soon as I open the lid or something happens, chances are we're not quite at equilibrium with a lot of them, but we could reasonably say that the amount of oxygen in the water is probably at equilibrium with the atmosphere, which is probably at equilibrium with the rest of the atmosphere, or close enough so that I have a good guess of how much is in there, right? That type of thing. Okay, so I've got a couple of illustrations for equilibrium reactions, how these go forward and backwards. I think I will save the illustrations for next time so I can tinker with MATLAB with you for a moment. But real quick, pH or the equilibrium systems themselves, the way we write up the reaction and kind of model it mathematically is we would describe some reaction between two reactants, could just be one, of course, A and B, going to C and D products, and the other way. So if those are our species and each of the lowercase ones, that's like how many moles of it we have or how many molecules are going to react, then the way we write our equilibrium equation is essentially products over reactants in this form. So we will define an equilibrium constant, KEQ in this case, as those products multiplied by each other. Make sure you are multiplying here. So C times D divided by A times B. And if you have the exponents, you put them there also. Now, of course, these are coming from these exponents, right? Okay, so that's how we formulate our equilibrium reactions in terms of like the mathematical sense of it. So I'm going to pause on that for the moment and bring up real quick some MATLAB slides on MATLAB. Okay, so last time I walked you through all this and I went through the website for this. You have these slides, and I'll repost with any notes I make real quick. So you can go and get MATLAB. There's instructions for that. So if you have not done so yet, I'm asking you to do so. You can just sign in with your @LSU thing here. You might have to register for it, and then you'll have it. There is technically a online version as well. Then you can go into the courses. I kind of showed you this. You'll go to each course that I've assigned. And then once you finish this course, you go up to the share certificate, download that PDF, and that's what you upload to show me that you've done your job, right? Okay, so I think that's all I had to say for that. Now, MATLAB itself. We've got just a couple minutes, so I'm just going to take a moment to show you what's going on my screen and show you what I would do if I sat down to work on something, or even just to solve a quick chemistry problem, right? So right now, what we're seeing is whatever the last time I used, which was teaching my other course, and I had a few things up here. These are different scripts that maybe I was working on. Maybe they were somebody else submitted. I think these were my stuff. And what I'm seeing is the text in one of these scripts and then a command window. Right now, what I might want to do is say, okay, I'd rather go over to our class. I don't think I have set up a MATLAB thing yet, but we're just going to say, we'll go to this computational thing and just pretend, we'll just use this spot for now, okay? I'm going to get rid of whatever script I had before, and now I have just the command window. If I wanted to make a script, now that I put the folder here, it would be putting it in that folder, into where I've organized my files into that spot. So you can just find a spot that works for you. Maybe you do it by assignment or whatever, and start working there. But you probably should do that because you don't want to be lost about where did I save all this? Or if you were to use a different computer sometime, you just want to make sure you're in the right space. Okay. Without going too much further into any of that stuff, what if I wanted to do my calculation here and say, this molecular weight for NaCl. I'm just gonna type MW NaCl. I'm gonna say I'm making that as a variable, and I'm gonna say that was 58.45, right? I just hit enter, and now one thing we see is over here on the right, we have some variable listed in our workspace. So now I can just type MW NaCl, and it's going to tell me what that equals. Okay, so now maybe I say volume 1 equals 250, but that's in milliliters. So maybe volume 1 new, I can say it's equal to volume, I think the caps matters, volume 1 times 0.001. That's going to divide it by 1,000, and that's going to say, okay, now I'm converting this from milliliters to liters. Another thing I can do, and what you'll find when you do MATLAB or any coding, is the syntax. The way you write things matters, and that's the thing you have to really figure out, is how the language works as a language, how you're talking to it. I'm going to put a semicolon here, and that's a little bit of syntax that'll just make it not give me the answer out. It's just going to hide it. It's going to do the calculation, but it's just going to hide it. So now it didn't say anything. But if I check volume 1 new,
You spelled volume wrong the first time.
perfect. And now it's fussing at me. So this is the type of mistake I'm gonna make, at least. Maybe you'll make it too, right? Okay, so let's spell it wrong. Volume 1 new, and now it tells me that's 0.25. So that's exactly what I wanted to kind of show you, is the type of stuff you're going to encounter, and it will fuss at you when you hit a typo, right? And when you use the semicolon or whatever stuff you are using, will impact how it works. It's stuff that you can do and you can use. It's just going to take some time of, oh, okay, that's how this works. What do I do now that I don't know how it works? Well, in this command area, there's also help file. So you can just type help. Usually you'd say help, let's say plot. And then it'll bring up the help file on how to plot stuff. And then it'll teach you a bit about the script and how the syntax is supposed to work. So you might get used to like looking stuff up that way as you go. Of course, you can Google it and things like that. And these training things are there for all of this reason. Last thing I'm going to end with here is you can also type CLC to clear the screen and clear to get rid of all those variables. Okay, so we'll end there. All right. Have a good weekend. We'll see you on Tuesday.
Thanks, Dr.